This is video 29.2. We'll be looking at how charged particles move in magnetic fields. In the last video, we learned how to calculate the magnetic force on a particle. The equation is F equals QV cross B. Now, some things to notice about it. First off, if the particle is not moving, there's no force. Second, if the particle is moving in the same direction as the field, there's no force, because the cross product is 0 for two vectors that point in the same direction. And most importantly for today, the force is always perpendicular to the velocity. And so let's imagine that we have a magnetic field that points into the plane of the page, and we have a positively charged particle initially moving to the right. Now, right-hand rule, point index finger in the direction of the velocity, other three in the direction of the field, you end up with a force that points upward. And that means that the path of the particle is going to start to curve. And a little bit later, the force will point that way, which will make it curve some more. And the result is that the path of the particle will make a circle. And that doesn't really surprise us, because we know that for something moving in a circle, the net force always points toward the center. It also tells us that the speed is going to be constant, just the direction will be changing. So now let's see if we can predict what the radius of the path is. Now, the only force that acts on this proton is the magnetic force. And because the velocity is perpendicular to the magnetic field, the magnitude of that force is just QVB. Now, also because it's moving in a circle, we can say that the net force is equal to mv squared over r. And we can do a little bit of algebra and find that the radius of a circle is equal to mv over qb, which is a result that you should probably not memorize, but you definitely need to know where it comes from. Also, notice the faster it goes, the larger the circle is. The larger the magnetic field, or the larger the charge, the smaller the circle is. Now, the problem with that is that we assumed that the field was perpendicular to the velocity. In other words, that the velocity was in the plane of the board and the field was perpendicular to that plane. But let's imagine instead that we have a magnetic field that points this way and a velocity that initially points that way. Now, the obvious thing is that because the angle between B and V is smaller, the force won't be as large, but it'll still be perpendicular to both of them, with the result that the particle will spiral around the magnetic field lines. And it's very, very difficult to draw those. So I'll try again in class tomorrow. But the important part is you get a helical path, not helicath, and it follows the magnetic field lines. This, for instance, is why the aurora borealis and aurora australis happen, because charged particles from the sun hit the Earth's magnetic field, start spiraling around the lines, and end up following them to the poles, where they run into the atmosphere and make bright lights. You should be able to qualitatively explain helical paths. You do not need to calculate anything for them. Now, the last topic for today is what we call crossed fields. where we have both an electric field and a magnetic field acting on the charged particle. So let's say that once again we have a magnetic field. It points into the plane of the page, and we have a particle moving through this, we'll assume that it's positive, moving through this field with speed v. Right-hand rule tells us that the magnetic force points upward. But if we want to make this move in a straight line through the field, we can pick a magnetic field or an electric field that will do that. And in order for this particle to move in a straight line, the electric force needs to point opposite the magnetic force, and that means the electric field, if this is a positive particle, has to point downward. Now you can see why we call these crossed fields, because the magnetic field and the electric field are perpendicular to each other, and they're also both perpendicular to the velocity. So we figured out the direction the electric field needs to be in order to make the forces cancel out. Now let's see what its magnitude has to be. In order for the particle to be undeflected, the magnetic force has to equal the electric force. And if the magnetic force, well, that's QVB because V and B are perpendicular, and the electric force is equal to QE, notice that the charge doesn't matter. As a matter of fact, you could take an electron, shoot it through these fields at the same velocity, and it would still go straight through. So positive, negative doesn't matter. Charge plus 1, charge plus 2 doesn't matter either. The only thing that matters is the particle's velocity, and as long as VB equals E, this particle will go straight through the fields. Now let's say that this particle were not going quite fast enough. So V is a little too slow. Now what happens there is that the electric force is the same, because the electric force does not depend on how fast the particle is going. But the magnetic force is smaller, and that means that this particle will deflect downward if it's positive. And similarly, if V is a little too fast, the particle will deflect upward. If it were a negatively charged particle, it would deflect the opposite direction, a positive one. So let's look at an example. This is problem 8 from your textbook. You've got an electric field of 1.5 kilovolts per meter, meaning 1500 newtons per coulomb, and a magnetic field of 0.4 Tesla act on a moving electron to produce no net force. Calculate the minimum speed of the electron. Now the first thing we'll say is that QVB equals QE, cross out Q, V equals E over B, plug in numbers, and you get 3,750 meters per second. That was really, really easy. But I want to point out one thing, and that is that the problem asks us to calculate the minimum speed of the electron. We assumed here that the velocity was perpendicular to the magnetic field. But if the velocity were not perpendicular to the magnetic field, what we would have to do is say QVB sine theta equals QE. Once again, we can divide by Q, and then we find that velocity equals E over B sine theta. Result of this is that for any value of theta other than 90, sine is less than 1, and that makes velocity larger. And so the minimum velocity occurs when that velocity is perpendicular to the field. Now tomorrow I'm going to check questions 3 through 7. Pay a special attention to the ones that deal with crossed fields. That shows up on the AP exam almost every year.